Hey everyone, welcome to The Explainer. Today we are unpacking a mind-blowing reality that almost no one thinks about, yet our entire digital lives literally depend on it. We're going to explore an invisible lifeline of time, constantly beamed down from space, that holds our entire modern infrastructure together. I know, it sounds straight out of a sci-fi movie, but it is happening right now, right above your head, and inside the devices you're using every single day. Okay, let's dive right in with a quote that perfectly captures the magic we're about to explore. If you want to know where you are, get an accurate clock. It's such a profound concept, right? We usually think of time and space as completely separate things. Like a map tells you where you are and a watch tells you when you are. But as you'll see, at the highest levels of physics and network engineering, time and physical reality are intimately, inextricably linked. To really wrap our heads around this, we're taking a macro to micro journey today. Here's the agenda. First, the core purpose of sync. Second, ultimate clocks in space. Third, turning time into space. Fourth, the relativity of absolute time. And finally, modern infrastructure lifeline. Let's get to it. All right, Section 1, Core Purpose of Sync, Eliminating Time Deviation. Let's start with the absolute basics. What actually happens when computer systems completely disagree on what time it is? Think about the sheer chaos of an unsynchronized state. You've got different systems running on their own internal clocks, creating what we call time deviation. In the digital world, this isn't just a minor annoyance like your wristwatch being 2 minutes fast. It's a massive risk for catastrophic logic errors. Imagine a bank trying to process a withdrawal before the deposit even registers because the server clocks are slightly off. It's total failure. So the ultimate goal, the sole purpose of synchronization, is to completely eliminate that deviation, tying all systems perfectly to a master terrestrial reference clock, like International Atomic Time or TAI. Now, we literally have to climb a synchronization staircase to reach that level of absolute precision. We don't just magically jump from chaos to perfect time. We start at the bottom, asynchronous, where the waveforms are just an unpredictable mess. The next step up is frequency sync. The repeating intervals match, but the starting points are still misaligned. Then we hit phase sync, where the peaks of those waves finally align, but they might be happening at completely different moments. It's only at the very top, time sync, where the whole shebang comes together. The frequency, the phase, and the epoch, the actual time of day, match perfectly. Moving on to Section 2, Ultimate Clocks in Space, GNSS and Atomic Clocks. Because to get everything on Earth to hit that top step of the staircase, we actually have to leave the planet entirely. Enter GNSS, or Global Navigation Satellite Systems. You know when you use GPS on your phone to find a coffee shop? You are actually interacting with the most famous application of atomic clocks in human history. Every single one of these satellites hovering out there carries incredibly precise cesium and rubidium atomic clocks. They are basically giant floating timepieces, continuously beaming a time signal down to us. And to keep them absolutely perfect, they're part of a closed-loop system, constantly being dynamically calibrated by even more massive, even more precise atomic clocks down on the ground. Just take a second and think about the sheer scale of this invisible infrastructure. These time signals fall 20,000 kilometers from their source. They drop past the Iridium satellites, past the Hubble Space Telescope, right through the Starlink network, past the International Space Station, all the way down past commercial flights until they finally hit your phone or a data center antenna. It is literally a constant, invisible rain of absolute time. And hey, it isn't just the American GPS doing all the heavy lifting here. We are relying on a massive global matrix of constellations. We've got 31 GPS satellites making up about a third of the network, alongside 24 Russian GLONASS satellites, 23 from the European Union's Galileo, and 27 from China's Beidou, forming the rest of the matrix. We are talking about roughly 100 hyper-advanced atomic clocks, forming a web around our planet, serving as the absolute bedrock of the modern world. Which brings us to Section 3. Turning time into space, the physics. We know they beam time down to us, but how does that magically give us our physical location? Let's unpack the trick physicists use here. I really want you to stop and think about this for a second. How exactly does a clock tell us where we are? It totally feels counterintuitive, doesn't it? Well, it all comes down to a brilliantly simple equation and the speed of light. The satellite stamps the exact time it sent the signal. Your receiver stamps the exact time it received it. You subtract the time sent from the time received. And because the signal travels at the speed of light, which is a constant, you just multiply that tiny, tiny fraction of a second by the speed of light, and boom, you've directly converted the precision of time into physical distance. Time quite literally becomes distance. So let's map that out into three-dimensional space. Once you had the distance from one satellite, you essentially draw a giant sphere around it. Do that with 3 satellites, and those 3 giant spheres will perfectly intersect at a single coordinate on the Earth's surface. That's you. But you absolutely need a 4th satellite. Sometimes the math of 3 spheres can result in a false intersection out in the void of space. That 4th satellite steps in to reject the false location, eliminate errors, and perfectly calibrate the time offset.
All right, Section 4, Relativity of Absolute Time, TAI, UTC, and Drift. Now, you'd think with all these atomic clocks and speed of light calculations, absolute time would be a totally solved, perfectly clean metric. But when you look closely, time gets a little bit messy. Think about International Atomic Time, or TAI. That is your absolute pure physics baseline. But we humans, we don't really like pure physics time. We want our clocks to match the sunrise and sunset, which fluctuate because the Earth actually wobbles as it rotates. So we created Coordinated Universal Time, or UTC. But to keep it aligned with the Earth, we have to artificially inject leap seconds. So UTC basically drops down like a staircase over the years. Meanwhile, GPS time stubbornly refuses to implement leap seconds at all. It just maintains a fixed offset. It's wild how even our most precise global standards are constantly drifting and adapting to the physical quirks of our planet.
Section 5. Modern Infrastructure Lifeline, the Ground Reality. Let's bring this journey back down to solid ground to see how our human-made infrastructure desperately, hungrily relies on these space clocks.
We call this the Holy Trinity of Services, PNT, which stands for Positioning, Navigation, and Timing. It is the absolute lifeblood of modern infrastructure. Power grids, telecom networks, financial markets, they all run on PNT. But here is the scary part. It has massive vulnerabilities. It can suffer from physical limitations, like losing your signal when you drive into a parking garage. But more terrifyingly, it's vulnerable to invisible attacks. Bad actors can use jamming to drown the signal out with noise, or use spoofing to send fake satellite signals that trick systems into thinking they are somewhere else entirely, or even in a completely different time. Want to know what happens when those systems fail? Just look at modern data centers. Imagine a massive distributed database, with users writing data in a US data center and trying to read it milliseconds later in an EU data center. These systems rely on a linearizability guarantee, which is basically this very delicate illusion that this massive global network acts as one single perfectly sequential server. If the clocks between the US and the EU are not synchronized down to the sub-microsecond level, the sequence breaks. A read request gets blocked, or it returns old data. That entire illusion of the single server just completely shatters. And this is exactly why the tech industry is shifting gears. For decades, we relied on NTP, or Network Time Protocol. It gave us millisecond precision with an error rate of 10 to the negative 3 seconds. And, that was fine for general IT. But today, for Meta's massive data centers, for high-frequency trading where fortunes are made in fractions of a second, for 5G mobile networks, milliseconds are an absolute eternity. We are being forced to adopt PTP, Precision Time Protocol. We're talking sub-microsecond precision. That is an error rate of 10 to the negative 7 seconds. It's a mandatory, non-negotiable upgrade to keep the modern world functioning. So if there is one thing you take away from this explainer, it's beautifully simple but deeply profound. The more precisely we master the invisible flow of time, the stronger our control over our distributed architectures, our physical space, and reality itself. Without that constant rain of precision from 20,000 kilometers up, our digital lives simply fall apart. Which leaves us with one final, kind of chilling question to ponder. We've built our entire civilization on the assumption that this sub-microsecond heartbeat is always going to be there. So what happens to our perfectly interconnected, high-speed digital world if those invisible clocks in space suddenly stop ticking? Definitely something to think about. Thanks for hanging out with me for this explainer, and I'll catch you in the next one.